Hello, this is Professor Kuehn, and welcome back to my lectures on astronomy, where we are looking at the work of Edwin Hubble. He wrote a book called The Realm of the Nebula, and we are reading selections from this. It's contained in a student's guide to the great physics texts, Volume 1, Chapter 26. You might recall that in my last lecture, we began reading about how the distribution of the nebula throughout the observed region of the universe is roughly the same. That is, no matter where you look in the sky, you count roughly the same number of nebula. So what Hubble does, he says, from now on what we're going to do is assume that even in the unobserved regions of the universe, that is, regions beyond which our telescopes can currently reach, let's assume that the distribution of nebula is also uniform. This is sometimes called the principle of uniformity, and it plays a very important role in cosmology, both at the time of Hubble and today. Now let's continue on page 324 and study the characteristics of the observable region of the universe. So we read together, the characteristics of the observable region as a whole forms the main subject of the present discussion. So he's going to be talking about what features does the observable region of the universe have. He says a brief appendix will be added indicating the kind of information concerning the universe we may hope to infer from the sample, that is, from what we can see right now. We are situated, by definition, at the center of the observable region. That is, when we look around us, we can see the same distance in each direction. Therefore, by definition, we're at the center of what we can see. Our immediate neighborhood, the system of the planets, or our solar system, we know rather intimately, but our knowledge fades rapidly with increasing distance. We know something about the stars, a little about the nearer nebulae, almost nothing about the more remote nebulae save their directions, their apparent luminosities, how bright they look to us, and the nature of the light which they emit. Information concerning the observable region as a whole is thus restricted to the most general features only, the distribution of the nebulae and the more conspicuous or obvious characteristics of their spectra. I'll say more about spectra in a few minutes. These data, together with the general laws of nature, which we assume to hold everywhere, are our present clues to the nature of the universe. Let us start with distribution. The nebulae are beacons scattered through space. In order to determine their distribution, it is necessary to know their intrinsic luminosity, that is, their candle power, both the average luminosity and the range. In some nebulae, if some nebulae were intrinsically 1,000,000 times brighter than others, as is the case with stars, the problem of the distribution would be extremely difficult. For apparent faintness would then be a very poor indication of distance. Fortunately, the nebulae are all of the same order of intrinsic luminosity. This information was derived as follows. So what he's telling us here is that by looking at the various nebulae, one can notice that some are brighter and some are dimmer, kind of like stars. Some are brighter and some are dimmer. However, with stars, the intrinsic brightness, how bright they truly are, varies over many, many orders of magnitude, something like 60,000 times. Some stars are 60,000 or more times brighter than other stars. He says the nice thing is that the nebulae do not vary as much in their intrinsic brightness. Most nebulae are pretty close to the same brightness intrinsically. And therefore, when one looks dimmer than another, one can be pretty sure that it is farther away than the brighter one. And now what he's going to do is he's going to explain how we know the intrinsic brightness of these nebulae. The nebulae are stellar systems, groups of stars, and some of them are so near that a few of the individual stars can be detected with the modern reflector telescopes. Stars are the fundamental criteria of nebular distances. We know something about stars, and wherever we find them, we can generally recognize their types, estimate their candle powers, and so derive their distance from their apparent faintness. In a dozen of the nearest nebulae, various types of stars are clearly recognized, and distances are rather accurately determined. So by looking at individual stars in some nearby nebulae, we can find out how far away those particular nearby nebulae are. So now he's going to go on to explain how that's done. For instance, some 40 Cepheid variable stars are found in M31, the great spiral nebula in Andromeda. Such stars in our own system average about 3,000 times as bright as the Sun. In the spiral, they appear about 150,000 times fainter than the faintest star that can be seen with the naked eye. A simple calculation indicates that the spiral must lie at a distance of nearly 1,000,000 light years away from us. Remember, a light year is the distance that light would travel in 1 year. So 1,000,000 light years would be the distance that light would travel in 1,000,000 years. Other types of stars which can be recognized in the nebula indicate the same order of distance, and hence we consider that the results are reliable. Such accuracy, however, is attained only for a very few of the nearest nebulae. So remember in last week when we were looking at the work of Henrietta Leavitt, we were talking about the method of cepheid variables in order to find the distance to a cepheid variable. That consisted in this, just to jog your memory. Cepheid variables, their period of flashing or period of oscillation was closely related to their intrinsic brightness. That is, the brightest cepheid variable stars flash very slowly with a long period. The dimmest cepheid variables flash more rapidly. So what one can do is, by looking at the periodicity of their flashing, one can determine the intrinsic brightness of that cepheid variable star, and then by comparing the intrinsic brightness to the apparent brightness or the apparent luminosity, one can determine how far away a cepheid variable star is located. That way you don't have to rely on parallax, which only works for stars within, say, 50 parsecs of us. So the cepheid variable technique provides a way of determining quite accurately the distance to stars that are very far away. So what Hubble's mentioning here is some of the nebulae that we can look at contain some of these cepheid variable stars. And by looking at the period of oscillation of the cepheid variable stars within these nebulae, one can determine the intrinsic brightness of those cepheid variables and hence how far away those cepheid variables are located. If you know how far away the cepheid variable within a nebula is from us, one can determine how far away that nebula is. So at least for some of these nebulae that are nearby us and contain cepheid variable stars, we can determine exactly, or to a good approximation, how far they are away. Now Hubble goes on as follows. He says, in several dozen other nebulae, we can detect a few stars but cannot recognize their types. That is, we can't be sure whether they're cepheid variables or not. Nevertheless, we have many reasons for supposing that there is an upper limit of stellar luminosity, how bright stars are, and that this limit, about 60,000 times as bright as our Sun, is in general attained and seldom surpassed in all the great systems of stars. Hence, we may assume that the brightest stars in all nebula are 60,000 times as bright as the Sun, and estimate their distances from their apparent faintness. The results may not be accurate individually, but they are reliable for statistical purposes. So this is a way that Hubble is going to rely on statistics throughout this paper. Finally, the great cluster in Virgo, remember the Virgin, a compact group of several hundred nebulae, is so far that a few stars can be seen in a few of its members, or so near that a few stars can be seen in a few of its members. These stars indicate the distance of all the several hundred nebulae in the cluster, the Virgo cluster. The 20 known clusters, moreover, are all similar groups, and their relative distances were already known. Hence, the distance of the Virgo cluster indicates the distances of them all. In this way, it has been possible to assemble a sample collection of several thousand nebulae whose distances and hence whose real luminosities and dimensions are known. An analysis of the sample collection indicates at once that the nebulae are all of the same order of luminosity. They're about the same intrinsic brightness. They average about 80 million times as bright as the Sun. So in other words, by looking at these cepheid variables within some galaxy clusters, determining how far those are away from us, we can determine that all of these galaxies are roughly the same luminosity. That is, all these galaxies are about 80 million times as bright as our own Sun. So they contain about 80 million suns. Okay? So what he's going to be saying here is that although individual stars, some are very bright compared to our Sun, and some are dim compared to our Sun, when these stars are located in galaxies, the galaxies as a whole tend to have about the same brightness, and that brightness is that of about 80 million suns. He says now the brightest are about 10 times brighter, the brightest galaxies or nebulae. The brightest are about 10 times brighter than the average, and the faintest are about 10 times fainter. But the majority fall within the narrow limits from a half to twice the average of them all. So in other words, whereas, like I said a moment ago, individual stars can be 60,000 times as bright as our sun, galaxies tend to be no more than 10 times as bright as another galaxy or 10 times dimmer than another galaxy, and most are within a factor of 2 of the average. So there's a much narrower distribution of brightnesses of these nebulae than there are of the brightnesses of individual stars. He says the mean of any considerable number, say 100 nebulae chosen at random, will be closely similar to the general average. For statistical purposes, where large numbers are concerned, we may assume that the nebulae are equally luminous and that their apparent faintness indicates their distance. So once again, the idea here is that although there's a great variation of brightnesses of individual stars, the nebulae are on average are very closely the distribution of brightnesses are tightly distributed around the average. That is, there's not much variation in the brightness of the nebulae. Therefore, if we assume that all nebulae are the same brightness, then their apparent brightness becomes a good measure of how far away from us they are. And that's the technique that Hubble is going to use in order to figure out how far away the various nebulae are from us.